Hello, everybody. Welcome to the 7th lecture of Battlecode. So today's lecture, like the past 6 lectures, we've been working on our lecture player and slowly making improvements to it. This lecture will depart from that theme slightly. Our lecture player bot is pretty strong at this point. It incorporates most of the essential features of a Battlecode bot. It has MicroStrategy, it has some form of pathing, it has communication. So today we'll be talking more abstractly about some ideas for more advanced improvements you can make to your bot. So we're not going to spell out explicitly how these would be implemented in lecture player, and perhaps these ideas, as stated, aren't perfect for this year's version of Battlecode, but they can serve as a platform for thinking of new improvements for your bots. And in particular, today we're going to be thinking about more advanced forms of pathing. So we're going to be covering breadth-first search in particular, and we'll also be covering bitwise operations, building on what Aidan did at the end of lecture 6. Okay, so let's jump right into pathing. So we already had one lecture on pathfinding last week, but I'll just remind you of the pathing problem. So let's say we were a soldier over here, and maybe using the logic from yesterday's lecture, this soldier is able to figure out where the closest enemy is. Maybe in this case, it uses that symmetry trick we discussed last time and figures out that this archon over here is its closest enemy. So the soldier's goal now is to walk in its general direction. It wants to walk from here to here. Okay, so how does this soldier figure out the best way to go? Because our rubble is uneven, so it needs to find, has to have some sort of algorithm for, figuring out where to go. Otherwise, it might get stuck in very high rubble tiles. And that's very important in this year's Battlecode to have a good pathfinding algorithm. So last week, Jerry covered some bug algorithms, which can work quite well. But sometimes a more advanced algorithm might be needed if you really want to get an edge in pathfinding. So today we're going to be talking about breadth-first search, just explaining the algorithm itself in a context independent of Battlecode, because it really serves as a platform for a lot of these more advanced pathfinding algorithms like Dijkstra's or A-star and so on. And since a lot of you may not have seen breadth-first search before or may not fully understand the algorithm, that's what we're going to do first. We're going to discuss breadth-first search. So in breadth-first search, we're going to say, let's look at the soldier here. We're going to have a simple model of when we want to walk, just like in in Jerry's lecture, where either a tile has sufficiently low rubble that we're totally fine walking in this direction. So maybe these edges are all fine, but we're just absolutely not going to walk onto this high rubble tile here. So we have some sort of 0-1 threshold. We're either an edge is permitted or it's not permitted. All right. So this is set up for breadth-first search now. So we can think of this more generally as some form of graph. So we're just going to take Battlecode is played in a discrete grid, but just to explain the breadth-first search algorithm, we're just going to consider an arbitrary graph with nodes and edges, like this graph here. So if you haven't seen a graph before, these circle things here are called nodes, and the lines in between them are called vertices. And in our context, the lines in between them are called edges. Vertices are another name for nodes. And in our context, these edges are going to represent tiles which we're willing to go towards. So let's say we've numbered the squares somehow. Maybe these are the integer versions of locations, and these are adjacent locations, and the adjacent locations which we're willing to go to. So then we want to solve the shortest path problem. So the shortest path problem is very simple. We have some designated start node. So let's say our start node is node 1. That's where soldier currently is. And we have a goal, which is to reach, say, node number 7. maybe that's where we think the enemies are. So breadth-first search is an algorithm for finding the shortest path in this unweighted graph where the edges are all of length 1. Breadth-first search is an algorithm for finding the shortest path from the start node to the end node. Okay, so yeah, so breadth-first search is nice in that it's like completely correct. It's going to find the shortest path for you. And does anyone have any ideas, if you haven't seen breadth-first search before, any ideas how we might start doing this? How might we find the shortest path from 1 to 7, starting from 1? Like, it's a pretty difficult task to do, outright. Like, if you just check all possible paths from 1 to 7, that's going to be extremely slow. That could be like, the number of paths could explode. So instead, we're going to take it in steps. So the first question we're going to ask is, let's not worry about finding the shortest path all the way to node 7. What nodes other than 1 do we know the shortest path to? So we know the shortest path to node 1. It's just to stay where we are. So what nodes might we very quickly be able to figure out what the shortest path is? Like, which nodes do we definitely know the fastest way to get to? Does anyone have any ideas? There are a couple nodes in this graph which we definitely know the shortest path to. Okay, so yes, 2 and 9, exactly. So these guys, because there are no way, there's like once we traverse an edge, there's no way of like reducing our distance. There are no negative rubble tiles, nothing of that nature. So therefore, if 2 and 9 are adjacent to 1, then we have one shortest path to them. We know that we can get to 9 and 2 using a path of length 1. And we can argue that there's no shorter path, because you can't have a path that's shorter than 1. That would be length 0. And clearly, if 2 and 9 are different nodes than 1, we can't have a length 0 path. That's great. So we're sort of like, building up. We've got a little bit of information. Now that we've done that, now that we've figured out the 2 and we definitely, without a doubt, know the shortest path to 2 and 9, are there more nodes which we definitely know the shortest path to? Like, can we grow our breadth-first search even more? Like, what more? Yes, 4, 6, and 3. Yes, that's exactly right. So 4, 6, and 3. How did you come up with these nodes? So I guess it's sort of similar to how we came up with 9 and 2, right? These are the nodes. Yeah, they're directly connected to 2 and 9. So we're sort of like expanding this frontier of like nodes which are like a shortest distance away that we definitely know. We started with 1, then we walked 1 distance away, and we knew without any doubt that 2 and 9, the shortest path to them was 1. And then we expanded our frontier 1 edge further to 4, 6, and 3, because these are nodes that are directly connected to 2 and 9. So to spell out that logic in full detail, so we know that there does exist a path of length 2 to 4, 6, and 3. And we also know that there's no way there's a path of length 1 to these nodes, because if there were, we'd have discovered it in our first expansion. They weren't 2 or 9, so there's no shortest path of length 1 to 4, 6, and 3. Great. So now we definitely know the shortest path to 6 of the nodes in our graph. What next? Which nodes do we, now that we've expanded one step at a time, which nodes do we know, we definitely know the shortest path to with our current information? What nodes can we definitely fill in now? All of them. Yeah, exactly. We can fill in the rest of the graph. So 5, 8, and 7 are all adjacent to one of these orange nodes, one of the nodes of which we knew had shortest path of distance 2. So we can say now that 5, 7, and 8, all of these nodes are going to have a shortest path of length 3. So there are a couple steps here. We know there's a shortest path of length at most 3. We know there is a shortest path of length. There's a path of length 3 because they're 1 away from nodes which we knew had a shortest path of length 2. So all of these nodes have a shortest path of 3 or possibly lower. And we know it can't be lower because we'd have discovered it in our previous iteration, just like before. This is really cool because we just take it one step at a time. Every step is, like amazingly simple. But we've managed to solve a problem which initially looked a bit scary because, starting from 1 and going to 7, the simplest idea is to just brute force all paths. And that would have taken a lot of time. Whereas here, hopefully you can see that the algorithm, it's a lot snappier, it's a lot faster. And in fact, we only really consider each node of the graph like once. Okay, so that's the idea of breadth first search. And whoops, you don't need that. And here is another picture of like the concept of breadth first search. So we're sort of expanding these waves, starting from where we start, so starting where the soldier originally is. We're expanding in waves, only going along those edges which we wanted to go on, which lead to tiles of sufficiently low level. And then we have just one goal in mind, like maybe we wanted to get to this enemy here, but breadth first search actually just figures it out for everybody. That being said, if the goal we had in mind was, say, this node here, we'd be able to stop our breadth first search early, right? If node 7 was here, or if the node where our enemies were was discovered in like just our second wave, there's no need to continue the breadth first search further. And this may be important if you try your hand at some sort of breadth first search in Battlecode, because your goal location might actually be quite close. And maybe you'll be able to save in a lot of bytecode by stopping your breadth first search early if you as soon as you discover that node. So that's the concept of breadth first search, to expand any sorts of waves. But there's just one more perspective that I want to introduce that's kind of useful for implementation. So let's think about breadth first search from this perspective, where we have all of these nodes on the left, which we've already explored. So these are the nodes for which we already know the shortest path to. So we know with certainty what the shortest path is to these nodes here. And we're continuing to expand. And rather than thinking about expanding in waves, we're going to think about just drawing one node from these unexplored regions here. So we pick the next node to explore from this unexplored region. And actually, this is a really useful perspective in that if you've heard of other graph algorithms, such as like graph search algorithms like depth first search, or even unweighted graphs algorithms like Dijkstra's or A*, all of them fit this paradigm of you're only going to explore each node once, like exactly once, then you're going to mark it as explored, then you're going to pick another node, and so on. And the only way these algorithms differ is in how they pick the next node. So let's think about how breadth first search would pick the next node. And to do that, so previously we had this, this waves picture, which you might argue sort of tells you how you're going to pick the next node. But instead, I'm going to give you another way of picking the next node, by using a data structure called a queue. So a queue is a data structure that is first in, first out, which means that you can put numbers into this queue, like put a 1 in, then a 2 in, then a 3 in. And then when you take a number out of this queue, you take the node that's been in there the longest, just like a real queue. Okay, so how does this queue give us another way of thinking about breadth first search? Well, here's how we're going to do it. We're going to start at our start node, and we're going to look at its neighbors. So its neighbors are 2 and 9. And we're going to add them to our queue. It doesn't matter which way we add them. We just add all of the neighbors of our start node. Okay. Next, we're going to, in fact, here's I'll actually start a different way. Let's say we start with 1 in our queue. So let's start with the initial node in our queue. And now the first thing we're going to do is take the first element of our queue. So that's our start node. So we're going to take that away. And then we're going to do what we just described. For the node we just took away, we're going to look at all of its neighbors, all of the tiles adjacent to it, which we're willing to traverse to. And we're going to add them to our queue. So we have 2 and 9. And now we're going to do the same thing. We're going to take the top element of our queue. Now that's a 2. Let's get rid of the 2. And we're going to look at all of the neighbors of the node we just removed. So the neighbors are 4, 6, and 3. Seems familiar. We have 4, 6, 3. And we're going to always add these to the end of our queue. So those go to the end of our queue. Now what do we do next? We again take off the top node of our queue. So that is now a 9. So we get rid of the 9, and we add all of its neighbors. But really, there aren't any neighbors to add. Well, that's not quite true. There is a 1, which we could add. So one more thing we have to remember is let's remember, which nodes we've seen, because we don't actually want to return to that 1 there, because a path that goes from 1 to 9 to 1 is never going to be part of any shortest path. We don't care about that. So remember which nodes we've seen. And if we do that, we'll be able to say, okay, 1 is a neighbor of 9, agreed, but we really don't want to go to it. So we're not going to add that to our queue. Okay, now we still have more elements of our queue. We have a 4, we have a 6, we have a 3. So let's pop one of them out. So let's take this 4 out. We take the 4. Now we see the 4 next. And all this while we can be, we're visiting nodes in order of increasing distance. If we wanted to, we could keep track of what that distance actually is. So we pop this 4 out, and again, we add all of its neighbors. So we ignore the 2, and we see the 6, we add the 6. So, oh, no, we don't have the 6 either. So when I remember which nodes we've seen, we also remember which nodes are already in the queue. So the 6 is already in the queue, so let's not bother adding the 6 either. Okay, so the 4 pops without doing anything. Then we get rid of the 6. And when we get rid of the 6, we add a bunch of things to the queue. We add a 5, we add a 7, we add an 8. So we put all of these at the end of the queue, but they remain after there's 3, which is exactly what we want. If you remember the previous description of breadth first search, we want to visit the 3 before we visit the 5, the 7, and the 8, because we have a shorter path to 3. That's a distance 2, whereas it takes a distance of 3 to get to 5, 8, or 7. And this queue data structure does exactly that. So actually, if you look at the order in which we visit things, it will just read off exactly as these frontiers read off. First the 1, then a 9 and the 2, then a 4, 6, and the 3, then a 5, 8, and the 7. Okay, so we add the 5, the 7, and the 8, and you can see where this is going by now. When we add the 7, we'll be able to declare that it's of distance 3 away, and our algorithm will terminate. So, and similarly, we'll pop the 3, that's distance 2, this is distance 3, this is distance 3. So that's another way of thinking about breadth first search. And it's useful because when you implement this, it might be easier to implement it with just a queue. So it's a very simple perspective now. We have this explored, unexplored business, and we use a queue to figure out what the next node is to pick. So that might be easier to code than explicitly coding our first intuition for breadth first search, which is that we have one frontier and we have another frontier. So we need to build up the next frontier from the previous frontier. That could also work, but this may be a bit simpler to implement. Okay, so that's it for breadth first search. So I've explained breadth first search for those of you who haven't seen it before, and also this sort of idea of having some heuristic for what you're picking from your unexplored region is also the basis for algorithms like Dijkstra's and A-stars, which are more complicated algorithms that deal with the case where you may have weights on your edges. Maybe a 50 rubble tile is okay, but it's still twice as bad as a 25 rubble tile, and you want to encode that. That's what these more complicated algorithms do. Okay, but that's breadth first search. Does anyone have any questions about breadth first search, about how it works or anything else? Okay, so let us now move on to sort of thinking about how might we do this in Battlecode. Because it doesn't just, especially in this year's game, it doesn't just translate straight over because of something you probably all are very familiar with at this stage, which is the limit on byte codes, like the limit on the amount of computation that any one of your robots does per turn. So the soldier over here, to execute a breadth-first search, to figure out what the shortest path is, given all these rebel values, to get to its enemy up here, its graph would have a node for every single tile on this map. And there are 3,600 tiles. So you're going to have to do like 3,600 quote unquote work to do a breadth-first search. And on a turn-by-turn basis, you have like 10,000 bytecode per turn, maybe a bit less than that. That's just totally infeasible. So yeah, so let's not, let's put aside those issues for a second and just think about how might we do this if we did have enough bytecode. So the idea of BFS and Battlecode I've sort of already introduced. So you could work backward from the destination as well, instead of working forwards from where you are. It doesn't matter. And yeah, once you see your destination, or once you've made a path, you just follow that route. That's the idea of BFS. And let's just think a bit more explicitly about what sort of state we need to maintain as we're executing the breadth-first search, right? Because there are a few details to check. There's a few details to think about here. One detail to think about is once we've found our destination in our breadth-first search, how do we know the route to it, right? Did we remember that? That's one detail to check. And also we just want to spell out exactly what we have to remember. So the first thing we need to remember is which squares have we explored. So we'd want to have either a 0 or a 1. Maybe this would represent false, and this would represent true for every square in a map. So you can think about how much, how much space this would take. I guess if you just had a separate, so I guess you could store this just an array of size 3,600. So using the trick that Aiden described yesterday for converting locations to integers, you could have an array of size 3,600 indexed by these location integers, and the value would be 0 or 1. This could be a Boolean array. Okay. The next thing is we need some state to explain, to help us figure out which square we explore next. So that's going to be our queue. Okay, so there are many ways you could choose to implement, a queue in your bot. Like, I guess, depending on how stingy you want to be about bytecode. So, but the queue works as described. It needs to support a pop operation and a push operation. One takes from the front of the queue, the other removes from the end of the queue. And finally, one more subtle aspect is when we're studying these graphs here, we sort of just assume that we knew everything about the graph. Whereas in Battlecode, you can't just query the rebel value of a tile that you can't see. But what you can do is remember which tiles, what the high rebel and low rebel tiles are as you explore the map and store these somehow. So basically, we need to remember the map. In our case, we'll just remember, again, 0, 1 values, because remember, we're using a pretty crude method of deciding whether we want to enter or a square or not, which is just some sort of, rebel threshold, like say 25. So we want to remember 0/1 for each square, and this is just remembering the map. Okay. So the issue with traditional breadth-first search is bytecode, right? 3,600 steps, with some, constant number of bytecodes for each tile we do. That's not going to fit in a single turn. Perhaps you could, so let's think about some ideas here. Perhaps you could split it across multiple turns. You could split your BFS across multiple turns. Another thing you could do is restrict how far you look. So depending on how your bot works, you might realize that you never really want to go on these grand adventures where your soldier starting here, plots out the entire path to here. Perhaps you just want to take local steps. Like maybe you want to do BFS just up to this radius here and get somewhere in that direction, and then do another BFS. This is something you could balance, so that's something to think about as well. And yeah, so I think that's basically where we're going to leave traditional breadth first search for this lecture. There is one more thing that we want to talk about, which is a distributed version of BFS. So like in previous Battlecodes, like I think this, like first in 2015, there is sort of this legendary strategy for executing breadth first search, which is to, you have a bytecode limit on each of your robots. What if we distribute the work? Like you have a bunch of miners doing all of your work for you and communicating them to your soldiers who are exploring. The issue with distributed BFS lies in how much you can communicate, especially in this year's game. So it might be a bit tricky, but we're still going to describe it in some detail for the benefit of like just learning about it, and also because the ideas you see might be helpful in other ways. So Elizabeth's going to take charge of that.
Hello. All right. I'm going to steal the screen sharing now. 1 second. Here, can you guys all see my screen? Garv, can you see my screen?
Yeah, I can see your screen.
All right, beautiful. So as Garv just touched on, the problem with running BFS on like any given robot is that it will take too much bytecode computation wise, and it can take like many rounds to run an extended BFS of the entire map. So the solution that certain competitors in the past came up with is distributed pathfinding. And I guess now I'm gonna give you like a quick overview of how this works. And if you guys want to like take that in certain directions, you can do that however you want. So essentially the idea is you want to use the remaining bytecodes or the computation power of many different robots to run a BFS together. So for example, if I have 30 robots trying to help me compute one BFS as opposed to one robot, then I'm basically cutting the computation time down by by a factor of 30. So how we want to distribute a workload, it's actually like pretty simple. If you guys are familiar with BFS, I guess if you watched the lecture that Garo just was just talking about, then at any given layer of exploration, different robots can explore different squares. And whether or not two different squares are explored by the same robot doesn't actually affect the correctness of your exploration. Therefore, we can essentially split up the workload and have different robots take different parts of it, and thus combining it together to form one pathfinding together. So we use this idea to distribute the workload among many robots, and you have to communicate using the shared array. We'll talk a little bit more about this. So what are some things that you need to communicate while trying to distributing the BFS workload? So first of all, in this year's Battlecode game, the map information is not available to every robot at any given point in time. Each robot only has access to the map information that it's surrounded by, like within its vision radius. So some things that you need to communicate are like rubble, resources, whether or not other robots exist in certain squares of the map, etc. So the reason why this is true is if I want to like use a robot and like do a pathfinding to the other side of the map, if I don't know anything about the map at that point, then I am not going to be able to do this. So some ways that you could consider doing this would be in the shared array, you can allocate like, let's say the first like, I don't know, 8 indices, you're like, oh, I'm just going to use this to communicate map information. And at any given point in time, there's going to be up to 3,600 squares in the map. You can use each bit for like each map or something, or like every 3 bits for a map square or something like that, and then just rotate across like many different rounds. And you can say, I guess, let's say there are like, I don't know, 120, they're like, how many bits do we give them? Like 16 bits each index. So if there are like 160 grid cells, you can say, oh, over 10 rounds, I'm going to communicate every single cell information using like 1 bit each or something. And then you will only be using like 1 bit, one value in the shared array to communicate the map information over 10 rounds. So that's like some ideas that you guys can use. The next thing that you would need to communicate in the shared array would be which nodes are explored versus unexplored. So this is somewhat limiting in the sense that you will need to have this information available for all the nodes at any given point in time. So given that you only have 64 indices to use, then maybe you would not be able to run a BFS of the entire map at any given point in time. However, you'll be able to do it on a local scope given the communication that we're providing you. Some other things that you would need to communicate to distribute the workload include which direction you take from each explored node. This is something you would just need to keep track of in order to backtrace any path that you end up computing. So as Gaurav has presented in like the BFS algorithm, you kind of like start where you want to end, and then you like layer by layer move backwards. And then in the end, once you go back to your initial starting point, you'll have to backtrace your path back to the destination. And to do so, you'll need to keep track of like which direction you're moving from for any given cell inside a map. So by doing this, robots with any spare computation left, they can just take unexplored nodes and then explore them and then mark them as explored. And then like the next robot in the queue that will have like more spare computation to run your BFS continuously will know to not explore those nodes. And in a sense that you can think about this as like having a queue of like all the nodes. And then as you're exploring new nodes and like finding more nodes that you need to explore, you can like put them onto the queue. And when you're trying to explore them and using your computation to contribute it to the BFS, you can like take them off the queue. And so that definitely requires a little bit more space on a shared array. In the past, when competitors actually implemented this into their robots, we were actually provided them a lot more space in the shared array. I believe in 2015, we let them have 65,000 indices instead of 64. So that is a big difference. However, I guess I put that in because basically, well, they're exploring nodes, they have to update a shared array on like what they did and like what the result was and yada yada. So for Battlecode 2022, we're telling you about this distributed algorithm because it's cool. And then here are some things you might actually be able to do with this. So because the shared array space this year is very small compared to some of the previous years, but this was actually incredibly useful. You might be able to do pathfinding on a limited scope. For example, as Gaurav mentioned, if you want to do a pathfinding in like a local area, or what's the most efficient way to get from point A to point B within like a 10 by 10 grid, then that might be able to fit within the shared array space. And then other distributed algorithms with the similar ideas, essentially you just want to like condense down to like what exactly you need to communicate in order to run these distributed algorithms, and just make sure that you're efficient with your space usage. There are definitely a lot of things that you will be able to do using this limited shared array space. And furthermore, I'm going to talk about some bit hacks and some bit operations in order for you guys to optimize shared space usage. As I've already hinted at, each index of the shared array, you have 16 bits to work with. If you're only using like 5 of them at any given point in time, then that's a big waste of space. So the next part of the lecture is going to be bit hacks. So I believe this was mentioned in yesterday's lecture, but as a recap, the binary representation of a W bit number, W as in like width. So the unsigned integer value stored in like X, given that X is like that representation, is going to be this. And it's relatively simple. Basically, you take this is going to be multiplied by 2 to the power of 0, this is multiplied by 2 to the power of 1, this is multiplied by 2 to the power of 2, etc. So this number in binary, this binary number represents 150 because this is going to be 0, this is 2, 4, this would have been 8, except it's a 0, so it doesn't count, and then this is 16, 32, 64, 128. And then you add the ones that have 1 in the corresponding bit location. So in Java, here are some bitwise operators that you might find useful. If you're not familiar with them, I'm just going to do a quick overview. So this is the bitwise and essentially it looks at each bit, and then the and is basically like if both of these are 1, then the result will be 1. Otherwise, it will be 0. So this last index, this last index is going to be 1 because it's 1 in both A and B, and these 4 are going to be 0 because only one of the two have a 1 in each of these indices. Or they're both 0. And then this one is also 1 because both A and B have a 1 at this position. And then otherwise, the rest of them is all going to be 0. And the next is going to be the bitwise OR, which is similar idea, except if either A or B have a 1 in any given position, that position is going to be 1. So this one, as you can see, has a lot more ones because it's just or. If either of these are 1, then it's going to be 1. And is like, oh, only if both of them are 1 is it going to be 1. And the next is XOR, which is exclusive OR. And essentially it's saying you have to be exclusive, like A and B have to be different in this bit position for this bit position to be 1. And that's basically what this represents. So A and B are different in the first and second indices, which is correct. This one is 1, this is 0, and then the second position, this one is 0, and this one is 1. So they're different. That's why these two will become 1. And then the next position is 0 because A and B have the same value in this bit position, which is also true. They both have the value 1. And then you keep moving down the line, and then essentially at any given index, if A and B are different, then it will evaluate to 1 with XOR, and if they're the same, then it will evaluate to 0. The next bitwise operator we're just going to cover quickly is the NOT, which is basically a complement. You just take all the digits and then invert them. That's it. So that's the complement. And then shift left, shift right, I believe the shifts are somewhat covered yesterday, but they're actually 2 shifts. 2 shift rights, so you guys need to be careful with that. Shift left is signed. It doesn't actually affect anything because you're shifting left, and essentially you just take all the digits and move them left by 2 and then fill in zeros on the end. So that's shift left. And then shift right, which is if you use 2 right angle brackets, that's sign shift, and then essentially what that does is it will move everything, cycle them rightwards, and then fill in the same digit as the most significant digits. So because the first digit of A is 1, when you're shifting right, if you're doing sign shift right, then it will fill in 1s in the beginning. And then if you use 3 angle brackets, which is unsigned shifting, you can see the difference is that it will fill in zeros in the most significant bit. So if you use the unsigned shift, it will always fill in zeros in the most significant bit, as opposed to the signed shifting, which will fill in whatever the current most significant bit is. So this is because in signed integers, you'll actually have a 1 leading. So when you're actually using integers, the first bit is actually the most significant bit is actually going to be 1 if it's negative and 0 if it's positive. And then I'm not sure if this was covered yesterday, but that's something to keep in mind. If you're only using 16 bits of an integer, you don't actually need to worry about it. But if you're using like all 32 bits, then the first bit will be 0 or 1 based on whether or not the number is positive or negative. So these are the bitwise operators that you might choose to employ if you want to make optimal usage of all the bits in the communication array. So here are some things you can do with bitwise operators. Some of this content came from one of the lectures in one of the classes I once took. It's pretty cool. All right, so if you want to set the kth bit in a number, so our goal is to take a number and then change one of the bits to a specific bit. So an idea is you can like shift this 1 to the kth bit, and then you OR it with the original number. So if you have x and you want to set the kth bit of this number x to 1, you take 1, you shift it over k slots, and then you take the OR of x in this mask essentially, and then your new number y is the result. So an example would be if k is 7, which means we want to set the 7th bit of x to 1. So this is an example of x. The 7th bit is highlighted in red. We can take 1, shift it over k steps, which gives us this mask, which is basically all zeros with a 1 at the index k. And then you take the OR, and ta-da, x is now the exact same, except the kth bit is now set to 1. So this is how you can sort of manipulate specific bits in your numbers. Next, if you want to clear the kth bit, it's similar, slightly more complicated, but it's similar. An idea is you can like shift something over, take the complement, and then do the and. And it's like similar. You have an x, you shift over 1 by k bits, so you shift it over 7. So now you have like the same mask that we had last time. You take the complement, so you actually flip all of this, and then so everything that was 0 becomes 1s, and everything that was 1 becomes a 0. So this is now your new mask, and then you take the and of this with x. So essentially what that does is anything in x that like matches the location of like 1s in this mask is going to stay the same because it's an and operator. If you and something with 1, it's going to equal to itself. So x and 1 equals x, essentially. However, this mask is not just like only 1s, there's a 0 in the middle. So this part, if you take the and operator, anything, so x and 1 is always equal to x, but x and 0 is always equal to 0. So that's kind of like some properties that we're exploiting here in order to clear the kth bit. So as you can see, if you take the and between this mask and the original number x, you're going to get the original number x, except this kth bit highlighted in red is going to be cleared, essentially set to 0. So can sort of, what if you just want to toggle the kth bit? So instead of like setting it to 1 or setting it to 0, you want to just like flip it. Like no matter what it was, you just want to change it to whatever else it was. So that's where like XOR would come in. It's like the same idea. You sort of create a mask by taking 1, shifting it over k steps to move it to the kth location, and then you just XOR x with this 1. So XOR essentially does a toggle, because if it used to be 0, XOR 0 and 1 is going to give you 1. If it used to be 1, the XOR of 1 and 1, because they're the same, is going to give you 0. So no matter what the original value is, you'll essentially toggle it. So it's like a light switch, you can flip it on and off just by doing XOR. All right. Oh yes, there's a question. For our shared array, it's unsigned integers only. Yeah. Well, you're passing in like integers. If you pass in something that's like negative, we're just gonna be mad at you and give you a game exception or something, game action exception. But yeah, essentially, you can use them as signed integers if you want, just by passing in a positive value, by having like a 1 in the first bit. You can like treat them however you want. Like you can interpret the integer however you want, but it's unsigned and non-negative theoretically. All right, hopefully that wasn't too confusing. Next, if you want to extract a bit field, which basically what that means is you want to take out a certain chunk of the bits. So let's say you have like 16 bits in a number. You're going to be like, oh, the first 4 bits are going to represent this, and the next 4 bits are going to represent this. How do you do that? So if you want to take a specific like some amount of bits outside of a number, what you can do is you just like create a mask and then you shift it. I've been using the word mask a lot without actually explaining it. It basically is kind of like, I don't know, it's just like something that I don't know how to explain it. You can figure it out. All right, so let's say you have this number x. You have a mask, which is these 4 digits are going to be 1 and the rest of them are all going to be 0. If you take the and, if you do the and operation of x in this mask, it's going to extract the digits of x that correspond to this part. So based on like which specific like bit digits you want to use, you can like hard code your mask and be like, oh, I want to extract the 3rd through 5th bits. Then you can like hard code a mask of like, I don't know, these 3, or something like that. So now you have your x value, you have a mask, you take the and, so you extract these specific bits, and now you have these bits, but you don't want them like, sitting 7 digits to the left of your least significant bit. So what you do is you're just going to shift it over 7 places, and then ta-da, you have extracted the bit field that you wanted. And you can do this with like no matter which chunk of like these numbers you want. You just have to kind of know how many digits in you want to do it, and then create your mask to match the corresponding location, and then also shift it over so they get moved to the end. Next, if you want to set a bit field, so these go together, where if you're just treating like some subset of the bits as like some information, then you want to like, take it out of a number or put it into a number. Then this is sort of the same idea. You can invert a mask to clear it, and then or to shift the value in order to achieve what you wanted to do. So here's an example. If you have an x and then y is like what you want to set this bit field to, the red stuff is like basically the parts you want to pay attention to. So let's say I want to set these 4 digits to these 4, this value in y. So what I'm going to do is I have my mask. It's still like, it highlights basically the 4 digits that I care about. If I clear these bits by using the same idea we presented earlier, you basically like invert the mask and then take the and, that essentially like keeps everything that's not part of those 4 bits, but clears these 4 bits. It's basically the same as this part, except you're doing it with, more than 1 bit at this point. So you do this, you basically clear these 4 bits from the original number, you take the y, shift it over, and then you take the or. So the or is the same as kind of setting the kth bit, where you just take the or. So that's here. It's basically combining the previous tricks and putting them together. So now you can arbitrarily set chunks of bits in a number very quickly by using bit operations. One thing that I don't know, maybe people are not aware of is that bit operations are extremely fast compared to normal arithmetic operations and everything else. So even if your code is like running slow, or if you want to like use less bytecode, yada yada, not just to like save space, bit operations would help you a lot, because bit operations are fast. Basically, any normal operation you do, such as like plus, minus, these are all under the hood converted into like bit operations, and a lot of them stack together. So if you can like achieve what you wanted to do with just using bit operations, it's a lot faster and uses less bytecodes. So here's some cooler things you can do with bitwise operators that are probably going to be a little bit less useful in Battlecode 2022 specifically, but because it's cool, I'm going to show you. All right, so no temp slot. This is basically if you want to swap the value of two variables without using a temporary variable. So the very, naive way that you would normally swap two variables, you're going to be like, oh, temporary equals x, x equals y equals temporary, but now you're using an extra variable. That's annoying. So, you can actually do this with just using XOR and without using a third variable. So how this works is basically because of this property where XOR is its own inverse. So if you do x XOR y, you're just going to get x back, because any variable XOR itself is going to give you 1, and then anything XOR 1 is going to give you itself. Wait, did I say that right? No, it's going to give you 0. Like y XOR y gives you 0. So x XOR 0 is going to give you x. There, that's what I meant. Okay, so how you do this, basically you take an XOR and then you take another XOR, set it into y, and then you XOR this back. So how this works is basically x equals x XOR y. So now y is, so x is the original x XOR with y, and then y, you're going to take that, XOR it with y. So you get x out of it. So now y is storing the original x, and x is storing the original x XOR y. And then x, you just take those two XOR it out, and now you get y out of it. And then here is a quick example where we have these 8-bit numbers for x and y. They start at these. We're going to run this first line of code, and now you have this where you see x has now changed to x XOR y. So that's this number over here. Y has not changed yet. And then y, you now XOR these two values and put it in y. So you extract the x out of it. And then the last step, you XOR the two values again, put it in x, and now you extract the original y value out of it. If it's a little bit confusing, you can look at this again a little bit later. Think about it a little bit. It makes a lot of sense, and it's really cool. All right. Next, some other cool things you can do that are probably less useful for Battlecode 2022. You can round a number up to a power of 2, essentially computing 2 to the power of ceiling of log n. So you decrement n, and then you take the OR of n, shift it over a little bit, and then shift it over 2 more bits, and then shift it over 4 more bits. And then 8, 16, 32, you increase it by a power of 2 every single time. And then the first decrement is basically to handle the boundary case of when n is a power of 2. This might be somewhat less intuitive. Maybe I should have added another table example. But if you think about it, so you have like this big number, and then you're trying to like take the most significant bit and like round it up, figure out which bit that is and round it up. So how that works is essentially these steps where I'm like taking a bunch of ORs is filling in every bit such that all of them are going to be 1. So let's say I have like my most significant bit. If I can fill in everything to the right with a 1 and then plus 1 at the end, that gives me a rounded up power of 2, if that makes sense. So like a number that's like entirely 1s plus 1 is going to give you 1 with a bunch of trailing zeros, and that is a rounded up number to a power of 2. So that's essentially how this works. And the reason why this goes down by a factor of 2 every single line is because, you push it over 1, you OR it, and then now you have guaranteed to have like 2 digits that are going to be 1, and now you can like copy both of them at the same time, and now you're guaranteed to have 4 digits that are 1 at the same time. So now you can copy all 4 of them at the same time. So that's why it goes on by a factor of 2 every time. And this decrement is just for the boundary case when n is a power of 2. Next, another thing, you can extract the least significant 1 bit of a number by using a complement. So basically, because integers are signed essentially in Java, so I have not thought this through extremely well, but if you're dealing with signed integers, the binary representation of negative x is going to be not x plus 1. That's just by definition, because -1 in 2's complement, or the binary representation used by computer languages, is just going to be like a string of 1s. So like every bit is going to be a 1. So that's -1. So that's why negative x is by definition going to be the complement of x plus 1. So then if you want to extract the least significant 1, essentially By that, I mean like you want to find the one digit that's like the smallest out of everything that exists. So you have like 101,000. You want the one that's like 101,000. You want to find this one. And how you can do this is you just run the AND operator on x and negative x at the same time. And because of this property, you'll basically extract the least significant one. So you have x, negative x is going to be this, and then you take the AND operation, and this is going to be the only bit that is going to be 1 in both x and negative x. So that's how you would extract the least significant one. And then another thing you could do, if you want to count the number of 1 bits in a number x, you can repeatedly eliminate the least significant one using, something similar to this. So using something similar to this, you can find like the least significant one, and then you repeatedly get rid of it every single time in loop, and then essentially you're going to be able to like count. And then R is going to be like the number of 1 bits in a number. So if you have like some number and you're using like different bits to mark the presence of like something, so this is something that can actually be useful. If you like have a number and you're communicating whether or not something exists using different bits, and now you want to be like, oh, how many of these things exist? I don't want to, very annoyingly shift every single one, even though that's totally doable. Here's a hacky way to do it very quickly. You basically single out like the and x minus 1, or I guess that's x and negative x, but does the same thing. It singles out like the least significant 1 bit and then gets rid of it. So then every time you run the loop, if x is not equal to 0, you're incrementing this count, which counts like the number of 1 bits that you've seen. So if you take x minus 1, it's gonna like remove this least significant 1 bit and swap out a lot of these things. And then if you take the AND of these, all of these digits from the least significant 1 bit onwards are guaranteed to come out at 0 after the AND operation. Because in the original number, this is going to be 1, the rest are going to be 0. And if you minus 1, then this original digit is going to flip to 0, and the rest of them are going to flip to 1. But if you take the AND operation, all of these digits are going to end up being 0. So that's how you eliminate the least significant one with just, this nice clean bitwise operator. So basically by doing that, you can count the number of 1 bits in the number x. And this is, the runtime is going to be like linear in the number of 1 bits that are in the number. Although, you could also just manually check every single bit. That wouldn't take that much longer, given that we don't give you that many bits to work with anyways. So yeah, that is kind of like a quick overview on some bit operations that you can do in order to optimize your communication array, or if you just want to, do some cool stuff in your code. Here are some more resources you guys might want to look at. It introduces a lot more bit hacks and other strategies that you can use to, make your code cooler or more efficient by using bit operators. So yeah. Credits to MIT 6172 bit hacks lecture, because I took a lot of stuff from that. Where's the Zoom? Okay, I can't find the Zoom.
All right. So thank you for attending. I guess that's it for lecture, right? Yeah.
All right, yeah. Thanks for coming. See you guys tomorrow, maybe.
Okay.